stuff. So I thought I'd talk to you a little bit about the evolution of it for a start. So we're trying to answer that simple question, which is, if not SQL, then what? You know, so where are we going with this stuff? Most of you have a very good understanding of your domain and your field that you work in. I see the world from a slightly different angle in that I work across many domains with both software development, data management, you know, and infrastructure and all these things, and there's obviously a story to tell about that, so I'm happy to share that with you tonight. So, let's see if I can operate this goodie. Right, so we have an interesting challenge. We have vastly underestimated the growth of data over the last 20, 30 years and the value that we place in that data. And what that means is that we've got to really rethink the way that we approach the problem. We are really rubbish at figuring out what's going to happen next, so we're quite bad at predicting the future. So we have lots of data, no knowledge about the future, right? And that means we've got to really think about how we deal with some of this stuff. So how can we prepare ourselves? So what I'm going to do is I'm going to take you through a bit of a whistle-stop tour of the history of information and where it comes from. We'll talk a little bit about storage and structure, about how we manipulate data, what we can do with that stuff, what's going to happen next, the types of tools that we see and the trends that I think are important for us to think about. And then hopefully during that process I'll answer your question. If I don't, then I'll leave plenty of questions on to talk. So my conversation is going to be fairly broad and generic, but you can ask very specific questions if you want. So, in the 60s, there was the first sort of commercial idea of a database started in the 60s with American Airlines. They had a flight booking system, and it was not relational data at that point, but it was a structured hierarchical storage system. But it's only in the 70s really that the concept of relational database management systems came about. And of course, what makes it an RDBMS is the idea that you have a schema and that you have storage and that these two things are separated from each other. And that means that you can then do interesting stuff with information. So you have a software system and you can talk to that software system through, or to your hardware, to your storage through the software system, query data, get data back out. Right? Then we thought we had it all cracked, and then of course in the 80s the personal computer came about and radically decentralized access to data, and everybody started buying PCs and started dealing with all of this stuff. And then we, you know, that boost in the sale of PCs started pushing people into innovating about data, thinking about how this stuff, how we can access data and what we can do with that. Then soon after that, the internet became popular, and we now had the access, we had the means to share information, and we very quickly started doing so. And then while we were sharing information, you know, these database systems that we built started evolving. So by the 80s, we start seeing some of the bigger players that you know in the market. So DB2, you know, those kind of things, IBM have their play. SQL becomes a standard, and we start using that to query information. Then the internet really boosts our ability to do this work, and suddenly, because we can do stuff with data, what do? We figure out how to shop. Right? So we start building Amazon and all the big shopping centers, or you know, all of this stuff, and we start boosting our interest in how we use data by simply doing online shopping, and that's the biggest change that we've seen probably in how we manage data. Right, so between 2000 and today, everything explodes rapidly, and we now do everything with computers. We do every task, the mobile phone introduction, you know, all of this stuff really explode with what it is that we do with information. So that's the state of play, where we are. In 1986, if you think through that little journey that I've just shown you, we stored digitally about 0.02 exabytes of data worldwide. By 2005, we start the digital age, which is where we do roughly equal amounts of digital data and analog data. Then we explode into 295 exabytes in 2007, suddenly from those little circles that grow bigger. And the prediction is that we'll reach 112 zettabytes, which is this giant blue background, and falls completely off the screen by 2021. So that's really starting to tell us that there's a rapid increase in the way that we do it. If you look on a graph, it has a proper hockey stick and it jumps straight up. So, knowing that all of this stuff is happening, how can we then try and understand what it all means to us and how we do work with data? So, at a high level then, we need to understand how data storage works, and I think this is an important concept for developers who tend to not understand how databases work. And if you're already a DBA, then you probably understand this stuff. But I want to share the information anyway. So, back when magnetic media just started out, the floppy disk, tape drives, floppy disks, what we learned to do there was to store data using sectors and tracks on a disk, and to then store that data in blocks of data, so 512 bytes of data, and then you could probably get 2 or 3 database records in that data, or stored in that block, and then you'd have to find a way to get to the data, which is on a disk, and the way to do that is to load that into system memory, into main memory. And that block storage model sort of transports into modern computing, and they actually haven't changed that much. So we haven't really modified the way that we store data since we invented hard drives, since we invented these things. So the block storage model sits in almost all IDBMSs today, and even some of the more modern technologies. To work with data then, you've got to put it in main memory, so we load it off a disk. It goes into RAM, as most of you know that. So at some point RAM became an interesting thing because it became cheap. So we bought lots of it, which meant that we can do processing. Right? So this is we can do all of the work. And then with that evolution came solid state storage. And with solid state storage, that meant that we can write data faster, read data faster from our systems. So we then slowly invented faster internet and broadband. Now that we can do reading of data, storage of data, manipulating that data in main memory, faster storage, faster transmission, it sort of fuels this growth in data. Then of course we invent the cloud, which is just massive scale storage. And with fast internet, we can push data into the cloud, and that explosion continues. So there are some challenges that come with it. Our concept of security changes slowly. It's worth knowing about these things. I'll talk about it a bit later. So if you now have data and it's stored on disk, and you can get it off disk and you can put it in main memory, you still need a way to find out what to do with the data or how to get to the detail. So this is where we start introducing structure or data structure to this. Most people know this as an index. So if you're a DBA and you understand what an index is probably one of the things that you see on the screen there. There are 2 types. There are hash tables, and really what hash tables do is they encode data into a smaller piece of information so that you can point at another piece of data on a disk, which is fairly simple. I think it was in 1980s, 81, I'm speaking in the correction, we invented proper binary search trees. And really what that says is that we can organize our index, we can decide where to put data and start doing things like sorting by storing things that are big on the one side and storing things that are small on the other side, or at least pointing to those data structures. And then eventually we invent the B+ tree, which optimizes this whole process. It's quite a clever piece of software, but it really is that piece of software that creates the ability for us to get to data and to be able to search for data. And virtually all systems today either have a hash table based structure or linked list and or a B plus tree as the basis for all of the searching and storage. Right, so B plus tree is really, both of these require that you point at data, so you have two different structures, and if you're a DBA that you'll have an index file, you'll have your main data file, and those two things are loaded to memory separately, and then you use the one to access the other. So we point at data, still at those blocks that we were talking about earlier, and this really enables us then to be in that DBA domain where we can do work as a database administrator. So by knowing these things, you can be a DBA, you can do that work, you need to understand where you have that data from, how these block stores work, how you index, and how you store and retrieve data. So then we get into the domain of data processing. In order to process data, we need to have that data in main memory or some portion of that. So we bring that back into RAM, as you all know, and that's where we can have access to the data to start doing something. So we've now indexed our information, we know where it is on disk by giving access to programs and algorithms in the memory. We can start doing interesting stuff with the data. But immediately we have a problem because we're trying to search through data. So if we search through data in memory, it's still sequential, it's still the same way that you see it on the disk. Still have to traverse all the blocks to try and figure out where the data is. So by using those indexing structures, we can be efficient at getting to those blocks. But what we don't know yet is how to get to the data that's interesting. So we start creating interesting memory structures. And these memory structures are things like the dictionary. If you're developing, you probably know about these things if you've written code, dictionaries, hash tables and linked lists, trees, and the various memory structures that you can use and that you can manipulate to get to either keys or values or allow you to do some sorting and stuff like that. So, with processing speed slowly increasing as well, following Moore's law, we have more and more capability to deliver, insight into how we process data, and we can see an explosion of data processing software and the way that we work in that space. Sorry. Just move on here. So these algorithms are the things that start telling us about how to sort information. So if you've ever heard of bubble sort or merge sort, all these things, very basic algorithms, these are the things that tell us how to get to information. So we're now starting to order the information, and of course if we want to save that, we take it back out of main memory, we feed it to our database, and off it goes. Right? It gets saved, and we've made those changes. So slowly but surely, of course, the processing power that we use becomes cheaper, more capable, faster. So we see this massive explosion into data and the rise of IoT, or Internet of Things, as we get sensors that are cheaper and cheaper. Glenn and I talked about a site called Banggood. It's worth going and have a look at it at some point. On there, you can buy today, you can buy an Arduino Uno little computer and a pack of 12 sensors for under £20. So you can really go and start putting data out in the world. And that's one of the big changes that's happening. So, manipulating data then. So we figured out how to do storage. We figured out how to do, how to get to that data, do a bit of indexing, start thinking about how to get to data fast. Mainly those things were driven by the fact that we had mechanical drives and slow technology, but of course as we go into solid state storage, those concepts start disappearing. But if we want to do something useful with the data, we need to manipulate that data in some sort or some way, so we try to start doing work in the data manipulation space. And really what that means is we create the ability to start mapping data. So if you're a data engineer, you'll know that you are talking about things like bar chart and text fields and things like that, date time. If you're a software developer, then you're more interested in how that applies in your software and how you store and move that stuff around in memory. So in order to run that software, often you end up in a case where you want to map data from one system to another system, and that really means changing that data type, which is how you modify things like integers to doubles, or modifying strings to dates, for instance. So, because we're human, we tend not to write everything down or type everything into a box. So we usually end up having to clean this data, and the reason why we do that is because there's a commercial business usually that's demanding that we have data that we can make sense of. So data cleansing then is really the process that improves the quality of that information by either adding missing information or checking the value of the information that you've got. And we can then do matching and reconciliation, which is to bring all of that stuff back together into a congealed common data set that we can do something useful with. So at this point in time, you've now got all the basics to be able to do data storage and manipulation. And this is where the paradigm of extract, transform, and load comes in. So if you're a data engineer, you know that data starts, from one system potentially, can be moved into another system, and that's the ETL process. Data in this state, when you have data that has a value that is created in time, becomes data that is in time, and that's an important concept if you're an analyst, to know that your data has a time dimension to it, a time value to it. Right, so continuing on data manipulation. Now that we've got the mechanism to process all of this stuff, we can start aggregating data, we can start collecting information, we know how to change the data. So we've got tools that have helped us to get to this process. We've got our databases, we've got our aggregation stores, we've got processing power, and we've got software that allows us to do ETL and transform information. So now we can start storing that data in bulk to be able to do something useful with it. So we can add a new dimension to data, and this is where the data scientist usually comes into play and starts saying, if I've got data that I collected on a Friday and I've collected data on a Tuesday, those are two different types of data. So by adding the dimension of days to the data, we can create data that lives over time. So we have data that we've aggregated that has a period of more than just one instance. In order to then deal with that data, we want to visualize what we do. And it's a very interesting topic, data visualization. Earlier on we saw that it's a whole field of science, and it definitely is worth looking at how that works. We'll talk a little bit about some of the software that we can use. And this is really, if you're a data scientist, you now have all the tools to do your job, and this is what you need to be able to work in that domain. There's a new concept coming up in the market now called the data engineer, which is a little bit more advanced than that. And I'll talk to you about that later as well. So, we now have all of this information, where we're heading with it. The scale that we've got this at, given people like Amazon and some of the other big retailers and some of the big banks, we really are talking about big data now as a topic. So in order to get to big data, really what that means is when you have multiple data stores in different formats with different types of content that are brought together across which you can search. So there's some really interesting technology out there. It really is a topic worth understanding and going into some detail, but I'm not going to go there. So it's a whole area of science in itself. Being able to have access to such large data sets is good news if you want to innovate, because you have access to large data sets, so you can look and compare things. It's really bad news for security and privacy because you can look and see things. So that's a problem for a lot of people to deal with that. And you can have a whole career in just this area of trying to make sense of where the security boundary sits. But of course, slowly, the competition that we have to make more money drives the cost of these things down, and as processing power keeps on increasing, the cost of storage and manipulation changes. Clever people come up with a security requirement, and we invent blockchain. Lovely technology. Somebody mentioned today to me that it's called the next snake oil of data. So there's a little bit of misunderstanding about what it really does. I think that's a very interesting conversation to have. I've got a lot of information on blockchain and this application, so I have to talk to you about that. And of course then, as our tools improve, we certainly get to the point where we start introducing machine learning to what we do and how we apply data. And with all of this stuff, we can add a new dimension in, which is the idea that data can be processed in real time, often from these IoT sensor sources. When data gets processed in real time, we call that data through time. So the data is now traveling, and at any point you can make the choice, because there's so much of it, to either discard that or to retain that data. So, tools and trends then. So let's have a look at some of the tools. So all of this, what you see here, is either free or open source, or has a free starting point. So you won't see in my deck any of the big boys. There's no Oracle or SQL or IBM databases or sources or tools in here. The reason why I've done this is just to make sure that there's another option available for you, and it's worth having a bit of a look. I think relational database management systems, so RDBMSs, so the SQLs of the world, they're the most well known, right? They're the ones that sit at the top there. Maria is an enhancement of MySQL. I've used SQLite as a developer a lot when I was starting out my career. That's still around. It's version 3 something, I think. These are very interesting pieces of information. Firebird is doing lots of real-time data at the moment. So really what relational databases are, then are data stores, block stores, with indexing that allows you to draw a relationship between two sets of columns and rows. And that's really what the technology means. So the software in there, the indexing method, allows you to call out a relationship between two tables. Really simple. Document databases then, slightly different piece of technology. MongoDB absolutely dominates the market. I quite like RethinkDB as well. I've spent quite a bit of time with that recently. Very fast, very clever piece of software. Also open source, so worth looking under the covers. For document databases, really what that is a block store, but where the indexing method is now not pointing at a relationship, but just directly at the entry for that block store. So, or for the data block. The difference here is that those blocks are much bigger. I think the upper limit when Mongo was released was 2 GB for a block of data. So you could have the whole block accessible, and they've got a really clever indexing method that allows you to bring that block into memory. You can store anything in that container, so it doesn't have to be sequential data, it doesn't have to be tabular data. And this really helps developers work in a slightly different way, because if you have a structure, a memory structure in your software, there's no easy way to map that into a relational structure. So the two things clash, they don't fit. But with a document store, if you're a developer, you can just take your object, you can serialize it, and just dump it into Mongo in one go, and then you have your stored data as a pseudo memory model. So then there's some specialist stuff. I'll pull up Neo4j on there, which is a graph database. And Neo4j is the thing that people use to do WikiLeaks with, if you remember WikiLeaks. So what's interesting in Neo4j is it stores nodes, only a very simple data type really, it stores nodes and relationships. So it draws a graph, but you can attach data to both the node and the relationship, so the link between the two nodes. So you can have something like the names of everybody in here, and you can carry a link on every relationship between the people, and that data can have, that link can carry its own data. So it will say two people from the BCS, so the link can carry BCS, and that's the important piece. And you can do the same with other links. You can draw multiple links between different nodes. And what that allows you to do is, if you look at unstructured data, so the idea that you have lots of documents which are their own node stores or their own document stores. So each node can be a document like Mongo, and each link between those things can have an action between the two, so it can sort of start storing really interesting information about how you traverse data between different entities, and that gives you the ability to draw those really interesting relationships between things that are of the same type or have the same type of action applied to them. So there's a very interesting analytical model that you can use that for. So with these RDM inverses, the problem with traditional SQL databases is that because it doesn't map directly to your software in the way that you work in memory, it doesn't really solve that problem, and there's a lot of activity that has to happen between the software and the data store to be able to get data out, do something useful with it, and then put it back. So you'll hear the word object relational mapper or object relational mapping, which is really one of those algorithms that allow you to map from objects which are software memory models into that relational data structure. So I'll give you an example. If you've got just the people in the room and the addresses and the companies that you work for, there's three different things. So you can have person and your details, so name, date of birth, that kind of stuff. Your address, you can have one or more addresses. So in a relational system, you'll put in person and one or more address potentially. You'd have to point to those things. So you'd also create a relationship in SQL. So you'd say you have a foreign key, so something that points to the data in the table. And if you then want to add anything else, then you keep on doing that, but you end up with the equivalent of thousands of spreadsheets that are somehow related to each other but not connected. In a document DB, the same information can just sit on a person. So you can have a person, their details, all of their addresses stacked underneath, and any other information you want to carry about them, size of their feet, blood type, all that stuff. And you can just dump all of that into your database in one go. Then in things like Neo4j, you can do that as well, but you can now draw relationships between these models. So you can say this thing is related to that thing, to that document over there, in some interesting way, and they can carry their own data as well. All right, so then we start getting into the big data space. The market dominant system there is Hadoop. It's a really complex beast. It's got its own developer community. It's got multiple versions. It's got multiple layers of interest that you can go and specialize in. So you can specialize in just writing MapReduce algorithms. But that is its primary mechanism for indexing. So what that does is it says that I've got all of this data that sits in our system, in a source system, some are all source systems, plural, and to get to that data that what you need to do is you need to run some kind of an algorithm to go, is the data here? If it is, do something with it. So we'll collect something. So we start mapping our way across the data. And then what we do is we collect the information that we want out of those data sets and reduce that into an answer that we're trying to form by looking at all the data. So an example of that would be, in very simplistic terms, if you're trying to figure out of all the staff that you have in your company, what is the person who works the longest hours, person that works the least hours, given that they are on average working so many hours a day. So instead of trying to map absence into that dimension as well, you could just ignore that, and you write your MapReduce algorithm to just say, ignore absence, find me people on average that have worked the most and the least, and order them that way. So you then end up with a new data set, which has that data in it. And of course, you can store that in your data set as well, or your database, or in Hadoop, and then have access to that data. The other one worth mentioning there is Elasticsearch. So Elasticsearch is an evolution of the Lucene project. What that does is really mini Google, so a proper search engine, and it's really a wonderful piece of technology. It's worth looking at Elasticsearch if you haven't done so before. It's quite easy to install and start feeding data, and if you're trying to draw relationships between things that aren't, where your information isn't strict, so you want to have more of a fuzzy answer, you're not entirely sure what it is that you're looking for, then that's one of the better starting places. And of course, you can take Elasticsearch and any other combination of these databases, combine them, and have interesting bits that you can do to connect things together. Another specialist DBs, there's Redis, which is a key value store. It's a very interesting piece of software as well, in the sense that it just has 2 columns in principle for every table that you can create, and literally just has a key and a value. That value, by the way, can be a document like in MongoDB, but it's really designed to do very fast lookup of small things. So if you've got all the postcodes and all the addresses that go with postcodes, then a Redis store for some of that stuff is really ideal, because you can just run through all of the postcodes and get all the answers back that relate to those postcodes. Right, so that's one application of Redis. It's not quite the best answer, best way of doing it. There are actually other slightly different applications of that data, but I've seen that used in things like train ticket booking, where you're trying to look up all of the available tickets that you have in real time while people are booking at speed. So while the train line is running and doing thousands of bookings, what you want to do is have a very fast data store that just says, book this one for now. You can always take it out later, so just reserve it another bit. Right, so in the ETL space, I've worked with a few things. Kettle, I've worked with, and Kafka. These are Kafka's completely open source. It's worth playing with it. I tend to look inside these bits of software usually and start looking for the thing that makes it tick. If you don't know how to do that, speak to one of your developer friends and ask them to unlift or lift the cover for you and show that. They all have their own piece of work, I think, or their own very specific application. Some of them is quite good in the sense that they allow you to think about ETL in a slightly different way, so you can do, depending on your style, so Scriptella, for instance, allows you to type in words that help you do ETL. I think Knowledge is the other one that I saw that allows you to draw out your ETL, so depending on your type of interest. Right. Then for data processing, if you think back what we talked about data processing, this is that part where we do enrichment of the data. My favorite by a long shot is OpenRefine, which was a Google project. It's worth having a play with OpenRefine. It does 3 simple things. very well, and it's totally free, so you can't go wrong with that. And we use that in fairly large data transformations that we need to do, or where we know that there's a lot of processing, where we have a sparse data set that we're trying to fill in the blanks for. The other one that I've played with is Yawn, which is also quite a nice piece of software. It has more of a visual interface to do the work with. And then if you're a proper analyst or a statistician, then you really need to learn R, which is a language in its own right. Very like SQL is a structured type of query language for for statistical processing. It's worth having a play with that. On the data analysis side, I've worked a little bit with Pentaho. I do fairly little in this space, to be honest. And I've played with Flink. Flink, by the way, is also the speed of a fuse. If you haven't ever heard of that word, so Flink is a fast-burning fuse. And then there's a wonderful word for a slow burning fuse, which is a trage. So if you ever get bored, look up Flink on the internet and see what you get. For data visualization, I've played with Gephi, but by far the tool that I probably use the most is D3, which is its own programming language. It's really a visualization set that sits on top of JavaScript, and it is worth playing with that. But if you just want simple stuff out, you don't want to pay money, then Plotly and Zoho and Quantum, all these guys do interesting stuff. Quantum is about GIS, so if you're interested in mapping, have a play with that stuff. So then, with blockchain, so the key thing with blockchain is that it's a distributed data store. So it is the evolution of what we think the database is going to become. It's a little bit like when we started talking about the cloud. People always used to say, "Oh, it's just infrastructure managed by someone else." But I think most people now think differently about the cloud and how that works, and what you can do with it, and the scale that it gives you, and the certainty that you have with it. I think blockchain is on the same evolutionary path. I'm quite interested in blockchain because of the opportunity of securing information in transit out there in the world. The problem with blockchain is that it's encrypted, so the thing that makes it secure is also its biggest issue. Because if it is encrypted, somebody's got to store the keys to that. That's got to go somewhere, and I think that's partly one of the issues. So if you've heard about Bitcoin, that's an early implementation of the blockchain, and I've had a conversation with a friend. There's a story doing the rounds that somebody has, in the very early days of Bitcoin, bought a whole bunch of Bitcoins, and they were pennies each, and then lost their PC, which meant they lost the secret key for all that stuff. So they can't unlock it. They are the owner, but they have no access. And so that's a bit of a problem as well. So I don't think we really understand where blockchain is going with these things. There's some really big challenges to solve, but certainly for me, it's one of the more interesting parts of my day job. Machine learning is then the next evolution of how we do that data processing side that we were talking about, which was just single pieces of software doing stuff. Machine learning is radically changing the way we access information and the way that we do analysis on data and information. There's a very interesting couple of students, I think in Berkeley in the States, that's currently looking at whether rats have a language. And so they record in ultrasound, record all of the data during the course of the day, and then they enrich that data a little bit by having a video feed and recording the time that they feed the rats. So they go through the whole process, record all of the information, and then they listen in the ultrasound to see if there's any chirps or squeaks that come out at the same time as the rat's being fed. So they fed all of that information into a machine learning system, which then started showing them where to look for these chirps and start finding duplicates and start finding like little patterns that they've done. It's taken quite a while for them to do so, but they are starting to get to the point where they think that rats do have a language, a fairly simplistic one, but they're trying to quantify what that means. And of course, there might be a time in the future that we can speak to rats because of machine learning. Not that I think it's very interesting, but it's worth knowing. So they use IBM's tooling, but if you're looking for something interesting in that same space, Ludwig is worth looking at, because that's been open sourced fairly recently. There are quite a few of these OpenMLs fairly well known. And then some more specialist ones like Cafe, definitely worth having a play with machine learning algorithms. If you don't understand machine learning yet, I make the distinction for myself just to stay sane, that machine learning is the technology that we're talking about. But when you apply that technology to something, that's where I start calling it AI. There isn't a good answer, by the way. This is all fairly new stuff. Different people have different ideas around this. Right. Then trends. Have I answered the SQL question, by the way? Anybody uncertain about whether we should use SQL or not? I don't think I've answered the question yet, so I'm going to answer it for you in a minute. So these are the trends that I can see. I think data, because of its ubiquity, because of the sheer scale of it, because of the sheer way that people work with information, because you have people who are interested in doing strange things with data, I think we'll see more and more data just becoming available as free open data sources to do stuff with. So you'll be able to buy data as a service the same way that you buy infrastructure as a service or software as a service. So the question for me is, how do we validate that that data has truth in it? So I think the trend is certainly going in that direction, but I think this is probably where machine learning starts helping us, when we start validating data sources across different suppliers to start seeing if there's, if there's an ethical response in there. I think it's a very interesting field to look into as well. There's certainly, the government does a lot of open data where it makes data available for free, not necessarily as a service, but for you to go and experiment with. It's worth just going on Gov.uk and searching for open data sets. There's some wonderful things to look at, including mapping and strange things like all of the potholes in a council or stuff like that. So worth having a play. I think tooling and automation, the ability for software and the ability for tasks to be automated is definitely rapidly on the increase. I can see more and more of our day work and of our staff talking about no-code or low-code solutions. So we don't write software anymore, you build software. That's definitely the case. I mean, even Microsoft Office has low-code or no-code solutions in it for doing fairly simple tasks. Worth playing with that if you've got an Office account, by the way, just for making some of your day tasks simpler. Sending a reminder, doing this. If you're interested in what IoT can do for you, have a look at IFTTT, which is if this, then that. Wonderful little thing you can download it as an app on your phone, and basically you can do clever stuff with that say, when I get near the office, remind me to pay my parking ticket. So really simple thing. Or if I get home, or as I get close to home, turn on the lights. You can do that kind of stuff. So we can start acting in the world more and more, and I think that trend will continue. So here's probably the answer to that question then. So I think we're moving from the concept of structured query languages, where you sort of interrogate a system and then it gives you a result back. It's usually a bit of an anticlimax, if you do it a lot, to being able to put natural language into systems where context is understood. This is definitely something where AI is supporting that movement, and I'm starting to see interesting developments in just on the internet from the research that I do. So I think there's an opportunity here where we'll eventually talk to our software systems, or you'll go, Alexa, who's got an Alexa, by the way, that uses it? Just as a quick show of hands. Three people? Right, you should have an Alexa in every room, by the way. You should absolutely have an Alexa in every room. The reason why I think it's important, so everybody goes, oh, it's recording everything you say. Yes, it is. Nobody cares, by the way. Social media has completely taken privacy away, so don't even think that there's some evil source out there looking at the data. What they do is they feed that to a giant AI, which does a very simple thing. It learns accents. It learns, my slightly weird accent compared to the next guy's, and tests for accuracy, because you go, Alexa, turn on the light. Alexa plays your song, and you go, Alexa, turn on the light. And you keep on doing this interaction. They take that information and they are improving that voice recognition system. Same for Google, Apple, everybody that does these things. I think it's a very interesting change in the way we work. So machine learning, I think, then is the next big productivity tool for people. So to put that into context, a lot of people say that robots are taking over the world. No, they're not. Not in our lifetimes, they won't. So where I think machine learning is really heading, these things are fairly simple in a lot of ways. I remember from donkeys years ago where I wrote some games where very simple path following programs or algorithms that were really the start of machine learning. And there you try and outwit your player by trying to steer the little ghoul or the little troll in a different direction based on their actions, right? So that's really a type of intelligence. It's extremely basic. That's probably not even mosquito intelligence, but I think most machine learning systems are certainly not even close to being sentient. Before we get to general intelligence, I think there's a lot of work to be done. So I think that's 10, 15 years out at least. What is interesting though, is how machine learning is enabling us to go faster, act on these big data sets, get useful information out of them. So, as I mentioned earlier, that IoT is really cheap now. I think it'll become very ubiquitous. I think in the next 5 to 10 years, we'll start seeing devices in your shoes, devices in your jacket, in your clothing, buttons that have intelligence, because batteries are shrinking because of carbon fiber nanotubes, and we are building smaller and smaller systems for less and less money. So, we'll have a bowl of M&Ms, might be a bowl of sensors or something like that in the future. They'll probably track the meat, all the yellow ones or blue ones. So I think that'll come up. I think the one big thing, probably the controversial piece here is I think we need a new way to interact with software. And I'm not convinced that talking to systems are really the way we should do that. But we certainly need something different. Often science fiction drives this stuff. So if you watch Star Trek, then in the old movies they used to go, computer, Alexa, right? Alexa, show me what we're doing, or take us to warp 5, or whatever it is. Interesting idea, right? But they'll also have screens up everywhere. So is that the future that we're building? Or is there another thing we can start doing about how we interact with data, how we interact with systems? And I think there's a nuance in looming in the future. What that is, it'll be augmented in some kind of a form, so it'll be something that changes the way we see or do or think about these things, but I don't know what the answer for that is yet. So, I will answer your question then. SQL or not? I think knowing some of this information that I gave you tonight hopefully allows you to think about the application of the thing that you're trying to do. So if SQL has its place for the right type of work, right? You have to know what it's doing, what you're trying to do, and how those two things intersect with each other. Then in the back of your mind, you've got to keep in mind that there's a commercial driver for almost everything that we do. So, it has to be accessible, relatively low cost, which is why I showed you free or open source software. I think that it has a value if you understand that the data in there is relational and has those limitations. So what's good about SQL is the fact that we have a very long history with it, and we understand what to do with it, how to build a data store if you're a data scientist, how to apply a star or a schema, a star schema to that data to be able to add your time dimensions and all these wonderful things. We understand that. In terms of things like Mongo, we have a document DB. That's really where developers are driving us. So developers are saying, if I have data in memory that looks like this, can I store my data like that? And the answer is yes. That's where document databases have a place to play. Where it's harder to work with those kind of systems then is when you try and get that data analysis piece done. There you have to learn how to use MapReduce, and there's quite a lot of opportunity to apply different things to that. It's worth understanding how Neo4j works as a software, as a database, because of its nature and how you could apply that. It's quite an interesting tool when you start dealing with data that is time variant. So I talked about overtime and in-time data. We have a mixture of those two things. Have a look at Neo4j, it'll solve some of your problems for you. So hopefully I've answered your question. If I haven't, this is my conclusion then. So you have to adopt a learning culture, or learn to learn, because it's quite a hard thing to do, especially if you've got a day job. It's very hard to go and find an hour to just do something different that's not related to what you are specializing in. We have a lot of specialists in the world, and people think that that's the best answer. I'm probably one of the worst specialists you can come up with. I tinker on everything, I'll rip everything open, I want to understand how everything works. But the advantage of doing that is that you start seeing the domain that we're in from different perspectives. And I can't teach you that perspective, but I think if I can encourage you to go and experiment, then you have the chance to learn and evolve and do something new with data. The key, of course, is to do something with data. So, start today, make that commitment, and go and change the way you think. Crack open the box, see what's inside, ask questions, and then learn from that experience. And hopefully, you'll be the next person to put a trend out there, and start something brand new. Right, I'll leave that open to questions. Hopefully that was useful. Just a quick one, if you want to, my unplug there, if you want to contact me, I'm on LinkedIn. It's the only social media that I actively manage. Please tell me that it's because you were here that you've seen me, because I have a tendency to ignore social media requests because of data privacy concerns. I think for get a chance for that quote to sink in as well. Mr. Skinner passed away in 1990, but he was a very interesting psychologist and really kind of preempted, I think, what we're trying to grapple with around things like machine learning and robotics today. Right, floor is yours. Questions? Hello.
Thank you. I think you gave us a whistle-stop tour there, and I think you just hinted at some of the depths you could go to there. One of the interesting things, just to open the question, and things I'd like to get your thoughts on, is you mentioned quite a few different tools and techniques, this is better than that. In terms of performance, we're talking about a few percent difference in performance, we're talking about a magnitude difference. How much difference is there between the best and nearly your side?
So I think that those lines are blurring quite a lot nowadays. I I think performance is an intention of your design process more than the effect of what you've done. Right? So the effect of what you've done is always going to be degrading performance. You know, so it's always going to get worse because you're adding more stuff to it. And it's standing still. You're not upgrading what you're doing. So performance is always on the decline. The second law of thermodynamics, I think. So I think that's something to keep in mind. So if you want performance systems, design performance systems, and then keep that design up to date, right? And you'll have something that always performs. It's one of the biggest challenges we have in just building software systems is just that. On average, by the way, the average software system out there for an enterprise business, somewhere between 500 meg of data in their main database, 2.5, 3 terabytes, around there somewhere. British Library on about 2 terabytes, I think. 2 petabytes of stored data, but on their active database, 2 tera, 3 maybe, since I spoke to them last. So, but that performance activity is a design activity, it's not a technology choice activity.
Okay. Questions from the floor?
That's all. Gentlemen back there.
Oh,
I have just a couple of questions actually. The first one, maybe pretty quickly, and it's around Neo4j and that concept of nodes and relationships and being able to store data on a relationship as well as on the node itself.
Yeah.
Can you then sort of put in place relationships between those relationships and
Yes.
sort of iterate and
So
clear that up?
yeah. So if you think, talk in terms of SQL because it's probably the best understood. So if you have two tables, let's say you have, let me just think. So you have simple one again, people and addresses, right? So you've got a people table, right, or a person table, singular person table, and an address table, singular name. So I get quite pedantic about that stuff, by the way, for my developers. So tables are singular, right? But when you connect them, they can become plural. So you can then say, you can put in something called an intersect entity between the two things. So you can model the same thing as a graph relationship by saying that person and address, single key in address. So you have 1, 2, 3, 4, 5 identity keys, lots of addresses in, and lots of people in the stuff. So you have a many-to-many relationship. You can change that many-to-many relationship by putting an intersect entity in, and the intersect entity will just say people addresses, right? So it's creating a one on the one side and a many on the other side. So it's saying, well, person addresses, so you say all the people on this side connect to those addresses. So when you search now, so then you can put your search on the intersect, which is that relationship in the graph database. So that can carry data, and you can, if you put your index on the intersect, then you can have a simple index on the person database or person table, and a simple index on the address table, which means you can write faster into them. So if you're trying to do a lot of processing where you're rapidly changing those things, then intersect entities models the same behavior. Yeah. And of course you can create another table, or you can create another intersect that flips the relationship. So yes, you can have two connections. So you can say address people or address person, so all addresses that have multiple persons to them. So a company, for instance. Yeah, so you can model it the other way around. And you can add other stuff, so you can have company in there as well and start creating a fairly complex relationship between them. Yeah. Useful technique to know. Yes, and your second question?
So my second question was a more general one. So I'm from a red tech firm which is active in the data privacy sphere, and I come from a more of a legal background, a technical background, and I'm just particularly wondering about what you said about privacy not being such an issue, and I'm sort of coming at it from the opposite perspective, which is we've got this massively pervasive new set of regulations.
Yeah.
And that must pose a problem.
It's an ethical dilemma. So let's talk about very briefly about things like Snapchat. Yeah. So what is Snapchat? Social platform. You have a community of people who can subscribe to you. Do you know them? No. You share information with them. Is the information vetted? No. So that information carries secondary information. So if you take a picture of yourself in front of a presentation, then the presentation is encoded into your picture and has been transmitted into an open community of people. So privacy is gone in that respect, but it's voluntarily done so. But now if you're a legal firm, don't have presentations in public because you're exposing the information. So, so the ethical concern there is, how do you protect yourself from that kind of behavior? Well, it's a problem to solve. I don't think there are any good problems or good solutions to that. I run a legal business as well, or I have a product line which is a legal product line, and we have the same issue to deal with. So there it's more about protecting data, in the business. That data is usually through time or over time data, so it's usually data that has, think of a legal case and the case management of that. It's over time. We've collected time data across a period. Whereas things like Snapchat is through time data, and thankfully it gets wiped up after a while, because otherwise it would be a resident somewhere. So yes, but not a clear line. And I think that line will get blurred more and more and more as we go, because we are voluntarily giving our information away. So a simple question, just out of the room, if you get a letter that's posted to you, what do you do with the envelope? Yes? Recycling, really? But recycling.
Press and recycle the rest of it.
Yes, thank you, sir. Good answer. Yeah. Recycling has people on the other end, right? It's not an automated process. So you're literally giving that data away. So now we're talking about GDPR. Does it apply? Legal conundrum. Yes. Interesting for casework, though. Interesting commercial opportunity. Yeah. Just stay at the recycling centre. Yeah.
There's a question from down here.
I'm Jafar Al-Sad. I'm an entrepreneur and a data scientist. There's a point I would like to add and a quick question.
Yeah, of course.
So my point is in context of data access and high performance. I believe AMD has recently introduced an AI unit that helps with the memory prefetching.
Yeah.
So replacing the conventional algorithm that was used in the past. I'm not quite sure how effective this is, so this is an interesting thing to research. So my question is actually about Hadoop.
Yeah.
I don't fancy Hadoop much. It is useful when you have a huge data set that does not fit in the memory of one computer.
Yeah.
So you need to distribute it. However, because it is a mass-produced process, obviously, so the more nodes you introduce, the bigger the overhead. So where do you decide the balance between the speed up you will get and you make sure the overhead is not just huge, but there is a diminishing return on
Yeah.
That's
It's a very interesting problem to solve. I'm going to ask you to just go have a look at this, by the way. Have a look at Rapids when you get a chance. So Rapids is starting to use the thing that's making machine learning possible, the graphics processing card. If you didn't know that that's the thing that fuels all of this, right? Rapids is talking about data processing in graphics memory, in chip memory, right?
But GPUs still have limited memory.
Yes.
Memory compared to.
Yeah. So when we were very data constrained, and I'm talking about when I started writing code, which was on a ZX Spectrum 48K, I think, way back, 48 kilobytes of main memory to run your entire piece of software, right? Back to that conversation about it's a design activity and not a response. When you're reactive to your data solution or your data performance problem, you've got to go look at the design of it rather than at the effect that you see. So if you design your software to fit into 48K, right, and it can perform, then that's a known thing forever. So the only thing that then changes is do you need to keep that information forever, right? So now we start talking about housekeeping and all that stuff. I mean, you can't possibly aggregate information as a single person forever, but we do. We give it a good try. You know, who uses cloud storage for their mobile phone pictures? Yeah, quite a lot of people. Right? How often do you clean those up? No? Even the duplicates that you've taken? Yeah?
I use Raspberry Pi actually to force myself to
Yeah, that'll focus your energy, yes. Yeah, but they're getting bigger as well, you know, so you can run the Windows 10 on them.
I still have 1 gig, not 4K.
Yeah. No, it is. That's why I do Unos, just because somebody named them after me, of course. So, but if you have an Arduino Uno, that size has stayed the same for quite a long time. No, it is definitely, it's the same answer. You've got to design for performance, you've got to design for scale, you've got to design for housekeeping. You've got to really think about the stuff that doesn't fall out of the sky. We had a very typical software developer dilemma. Something I'm still trying to teach my guys not to do is they start usually to design in the database. They start in storage. You know, it's a bizarre idea because what are you going to learn there? You're only going to learn how to store data there. So you've built a system that stores data. Yeah, that's the answer. So if you've got to really just think about the design, step back from it, go, is this a good idea? How do I make my systems performant? How do I increase the performance over time? If you can answer that question, you will design a different system. Yes, and you will have readers and Congo and all these things in layers probably on top of each other. So pull data out of Hadoop, stick it in readers, run through that, develop data processing, then decide whether you actually need the data. One of the other things that's not obvious necessarily to people, even data scientists somewhere, is you don't have to have a massive aggregation store where you then run through all your data and then count everything and then go, here's my answer. Right? You can count at source. So you can count where the data is generated. You can go, oh, this kind of thing. So the simple design principle is count at source. To say, my Raspberry Pi is generating data, and as part of generating data, every time that I add something, I'm incrementing a counter, and I'm also pushing that out. Yeah. So now I've counted, which is the result of your fairly heavy aggregation. Yeah. So you can count first and generate data at the same time. My first solution.
Thanks, another great presentation. I have a question about legacy data. I spend a lot of time and effort in my business sort of moving data from one system to another. I've seen it happen. Huge cost, huge time and effort.
Yeah.
At what point are we there yet in terms of obviating legacies, for some systems or not others, and what's it going to take?
So I'm going to kind of use his example to answer the question. When we had legacy systems, we were forced to design in a different way to be really efficient with the way that we store information. Right? Now, the behavior in general is that we don't do that because we're not cleaning up our photographs, as you all say. Right? So we're not efficient at storing data anymore. So I think that problem, the legacy is yesterday's data, by the way. I think that problem is getting worse steadily. So, and I think we're reaching out, we're clutching at straws like ML and all these things to try and solve those problems, to help us with dealing with some of this stuff. But the better answer, again, is to have an absolute intent to not create legacy data. Yeah? Or to very efficiently design what you're storing and doing with. Now, if you're in the space where you're trying to migrate information, the data sources you had back then. Yeah, so the data sources that you had back then, just 5 years ago, probably half of the companies that you got data from don't exist anymore. You can't necessarily validate that. The data in time back then had a value. Over time, it doesn't necessarily have a value. So, cut your losses is the short answer.
But you can design a system today to prevent a legacy system in the future, you think?
No,
No.
no, because
We're not there yet.
we're really rubbish at predicting the future. So, and we are, it's a fundamental problem. If I could predict the future, I wouldn't be here, I promise. You know? But it is a really big issue for us to deal with, because if you think about how, you know, we're doing this work, so you're building a system using the very latest technology, and then in 5 years, I know for a fact that that same system, unless you touch it every day and do something new with it, that system in 10 years from now will be a legacy system. You know, and given the pace at which we're accelerating this stuff, you know, there'll be a point where 2 years is an ancient legacy system. You know, so we are moving more and more into real time, and trying to deal with data as we go. The through time data, I think, is what's interesting. And if you can discard data, then do so, because, you know, we probably don't need half the stuff we store.
That's good. Okay, I think we've got time for one more question, so the gentleman back there.
I'm just interested to see data as a service. My name is Shinasa, I work as a business architecture consultant for a media company. I wanted to gauge, does that introduce smart contracts, or is that separate?
So smart contracts is really blockchain technology, is really the principle. Yes, you'll see that more and more. The problem with those things is, as soon as somebody figures out how to turn it into a commercial venture, they're going to do so. So what might be open source and free today might not be the same answer tomorrow. So it is a tough thing to do. So to pick that right technology. But you know, common sense says, you know, when we came in, we heard that there's no fire alarm. So if the alarm goes off, we've got to leave, right? That's a backup plan. So have a backup plan for your data as well. You know, whatever you think you're picking, solve some of that legacy conversation as well. Just design a backup plan so that you know if you suddenly have to move or the technology shifts underneath you and you want to stay current, that you have another option to deal with. Yeah. So why not have a plan B or a C or a D? If you can plan, just carry on. Yeah. Okay. It's only double the price, by the way.
That's good. Okay, so I think we've run out of time now, so I'd just like to join me in thanking you. Now we've got a small gift from BC.